Alright guys, so today 2.6 Notes Day 2 is talking about comparing quadratic functions. Alright, so the first thing we're going to talk about is concavity, whether something is concave up or concave down. Where does this appear? It always appears in the a value. So in standard form, we have ax squared plus bx plus c, right? So then the concavity will be known based off of the a value. In vertex form, we have a times x minus h squared plus k. Again, the a value at the front is going to tell us the concavity. Finally, we have intercept form, which intercept form is a, x minus p, x minus q, and it's always that a value. It tells us concavity. What does it tell us about the concavity? If a is greater than 0, which means a is a positive number, then we would be concave up. So it would look like this. Right? This is called concave up. Versus when a is less than 0, it would look something like this. And this is called concave down. Alright? Next thing we have to look at is the maximum and minimum points. This appears in the vertex. Okay? Specifically, it's the y value of the vertex. So, if we have something in standard form, then our vertex, as we know, is negative b over 2a. That would be the x value. And then to plug that in is where we would get the y value. So f of negative b over 2a would be the maximum. And it's specifically just that y value. Alright, where does this appear? In vertex form. Right, so in vertex form it's h comma k. So again, the y value, so the k value would be the max or minimum. And then in intercept form, it's just the direct middle of the two x-intercepts. So between the x-intercepts. Alright, so what do these look like? We either have a maximum. Alright, so if we're concave down, we would be left with a maximum point. Or we might have a minimum if we're concave up, because then we have something down here. So then this would be a minimum. Alright, next up we have the x-intercepts. So, where do we find x-intercepts? We always find them when we set any quadratic equal to 0. Alright, and then we solve for x. So those are the x-intercepts. What are the different ways we know how to do this? We know how to do this with the quadratic formula. We know how to do this with factoring. And we know how to do this with completing the square. Right? So where do x-intercepts show up? Wherever we cross the x-axis. Right? So we could have two x-intercepts. Or we could just have one x-intercept. And last but not least, we have the y-intercept. So where does this show up? When we are in standard form, hopefully you remember it's just the c value, so ax squared plus bx plus c. The c value is always the y-intercept, right? If we are not in standard form, so in any other form, you just plug in 0 for y, or x. Plug in 0 for x. That would give you the y-intercept, right? And where do y-intercepts exist? They exist wherever the quadratic is crossing the y-axis. Alright, so this is all just important information. Kind of went through it pretty quick, so if you need to grab some of that, just look at the key. It's all the same on there. So let's actually do the bulk of the notes here. So it says create the quadratic equation in the form labeled for each person below, and then graph the functions on the grid below. You may want to use different colors. So it says Alice has a quadratic function with a vertex of -1, 3, and a y-intercept of 0, 2. The hint says plug in everything you know and solve for what you do not know. You will need to use vertex form. So we literally know the vertex, so we know h comma k. The other variables in vertex form are just a, right? So we have y is equal to a x minus h squared plus k. We also know an x and a y, so let's just plug in everything. So our y value is 2 is equal to a, our x value is 0 minus h, which would be minus -1 squared, plus our k is 3. So now we can actually solve for a. So 2 is equal to a. That's going to be +1 squared plus 3. So we could subtract 3. We would get -1 is equal to a times 1, which is just a. So that tells us -1 is equal to a. So then this equation, when we're writing it, is y is equal to -1 x minus h, sorry, not h, we know h. It's -1, so x plus 1 squared plus 3 would be our vertex form. Okay. Next up, Ben has a quadratic function, y equals x squared minus 4. What form is this given to us in? All right. So technically, this is standard form, ax squared plus bx plus c. Just that b is just 0. Okay, so then it gets rid of the middle term here. So we can call this standard form. I'm actually going to change this color. We'll make it like a purple. So this is standard form. It says converted to intercept form. Well, if we factor this is a difference of squares. So difference of squares. How does that factor? That just factors into x plus 2, x minus 2. That would be our difference of squares. All right, next up, what do we got? Charlie has a quadratic function with zeros / x-intercepts of 4 and -5, and has an a value of 1/2. So the factor for +4 would be x minus 4. The factor for -5 would be x plus 5. So we also know the a value of 1/2. So then we have y is equal to 1/2 x minus 4 x plus 5. Boom. Alrighty. Last one here. Danielle has a quadratic function represented by this table, 0, 7, 1, 5, 2, 5. It says, hint, a equals 1 in this equation. What is the x value of the vertex? How can we use this to find the b value? You could also use your graphing calculator like linear regression, but you pick quadratic regression. So, let's do this one. Things that we know. 0, 7. What is this point? This is the y-intercept. All right. We also know the a value is 1, and we know 2 points here. All right. So let's plug in what we know. Why not? So we know the y-intercept, so we know c, so that's plus c. We could say a is 1, so that's 1x squared, plus bx, unknown, is equal to y, right? And so, sorry, we said c was 7. We know c is 7. We know the a value, so really the only value we don't know is b. So then let's plug in a point. So I don't know, 1, 5. So 5 is equal to 1 times 1 squared plus b times 1 plus 7. So 5 is equal to 1 times 1 is 1 plus b plus 7. So that's 5 is equal to 6 plus b. So we subtract 6. So that gives us -1 is equal to b. Sorry, 1 plus 7 is not 6. 1 plus 7 is 8, so we subtract 8 from both sides. Negative 3 is equal to b. So now we have all parts of this equation, right? Y is equal to 1x squared plus, or I guess minus in this case, 3x plus 7. Boom. And there is our equation. Okay. So for these, I'm just looking for rough sketches. Rough sketch, we're just going to go 3 points. So the first one, vertex form, we have the vertex at -1, +3. It tells us that the y-intercept is 0, 2. So 0, 2 is right here. Graph across the axis of symmetry. Okay. And now we can just draw this function. It looks something like this. The next one is Ben's function. Ben's function has a intercept at -2 and +2. Okay. We know it's opening up because the a value is 1. We need to find the vertex here. So the vertex is going to be at 0 because directly in the middle. So we're going to say y is equal to 0 plus 2, 0 minus 2. So that's y is equal to 2 times -2, so that's -4. So we go 0, -4, boom. Graph that. Sorry, that side was not as nice. Okay. Next one we had was Charlie. Charlie was in blue. This one we know the intercept form is +4 and -5, so over here. So that means directly in the middle of those two is -0.5, so y is equal to 1/2, -0.5 minus 4, -0.5 plus 5. So that's 1/2 times -4.5 times +4.5. Plug that into my calculator real quick. So 0.5 times -4.5 times 4.5. Gives us -10.125, so 10.125 is like right there. And then that's 3 points, so we'll graph it. And then our last one actually gives us 3 points. 0, 7 is 1 point. We know 1, +5, and we know 2, +5 as well. Okay, so this one, it's kind of hard to actually see this graph a little bit here. We might need to find the vertex of this point, so let's kind of do that. Well, we know that it's going to be between 1 and 2, so that's 1.5. So if we plug 1.5 into the equation, y is equal to 1 times 1.5 squared minus 3 times 1.5 plus 7. Let's see what value that gives us. 1.5 squared minus 3 times 1.5 plus 7 gives us y is equal to 4.75. So 4.75 is like right here. And now we have plenty of points to graph this function. Looks something like this. All right. Awesome. So that is just a quick overview of kind of what we're looking for with writing functions given different types of details. All right. It says whose parabola is concave down. So if we're looking at this, concave down would be opening down, so that is Ben. Right? If we didn't have the graph, how do we know? Well, it's because Ben's that's Alice. Sorry. Alice is yellow. Alice. How would we know if we didn't have the graph? Well, the a value is less than 0, so it's negative, right? That's how you would know that it's concave down. Who has the highest y-intercept? So it looks like Danielle. She crosses at 0, 7, so Danielle. Who has a y-intercept for a vertex? Y-intercept for a vertex, purple. Purple was Ben. And then who has the lowest minimum point? That looks like Charlie. Charlie is just the lowest on the graph. Finally, who has no real solutions? And that also looks like Danielle again, because she never crosses the x-axis. All right, so last little part here. Suppose Brett and Andre each throw a baseball into the air. The height of Brett's baseball is given by that function, negative 16t squared plus 79t plus 6, where h is in feet and t is in seconds. The height of Andre's baseball is given by the graph below. So let's kind of just label this. It looks like the vertex is probably right around here. I'm going to say that y value is approximately 75 feet, because 70 is about here. Yeah, so 75. Also, y-intercept, who knows if we need it or not, probably about 5 feet. X-intercept down here, that's another important point. I'm going to guesstimate the tick marks are counting by 0.2, so probably about 4.22 seconds approximately. So then Brett claims his baseball went higher than Andre's, and Andre says that his baseball went higher. Who is right? Support your answer mathematically. Well, graphically is Andre's representation. So we know Andre is about 75 feet. How can we do Brett's? So Brett, we have this equation. The maximum height would be at the vertex, so negative b over 2a. So negative b is negative 79 divided by 2a, which would be 2 times negative 16. I did not do that right. Let me write this in. Brett, negative 79 divided by 2 times negative 16. Negative 79 divided by negative 32 gives us 2.46875, and now I'm going to store that as x in my calculator and plug it in. So negative 16, 2.47 squared plus 79 times 2.47 plus 6, negative 16 x squared plus 79 x plus 6 tells us that Brett's ball actually at 103.5 feet in the air. All right, so who went higher? It does look like Brett, in fact, did go higher. All right. And that would be mathematically how to show that, right? You could also show that graphically by plugging the equation into your graph. Okay, but if it says mathematically, you would need to show this work that I just did. Okay. How long is each baseball airborne? Show work / explain. So this one doesn't necessarily say we need to show graphically or show mathematically, but we do know Brett's, right? The length that it was in the air would have been the point that it left his hand, so this 5 feet, all the way to where it hits the ground, so 4.22. Well, 5 feet is at 0 seconds, 4.22, so that means it has an elapsed time of 4.22 seconds. Approximately, right? We don't know exactly. Whoops, that's Andre. Sorry. I'm so sorry. I keep messing up here, guys. That's Andre. And then Brett is the equation. So the equation is a little bit more work. So mathematically, you would have to go quadratic formula. Or you would complete the square. Okay, that's how you're going to, that would be how you would get these mathematically. But what I am going to do instead of either of those, I'm just going to throw them into my graph real quick. So negative 16x squared plus 79x plus 6. Zoom 6, hopefully I see it. Nice, it does show up. Second trace 0. Looks like the x-intercept is equal to 5.0123. So how long is each baseball airborne for? Andre's is 4.22 seconds, and Brett's is 5.0123 seconds. All right. So I did that graphically. It was nice and quick, but you could also use quadratic formula or completing the square. All right, and that's all the notes for today, guys. It's really just a lot of comparing quadratic functions. Notice we compared Brett and Andre, a graph to an equation, and then up here we had a table of values, intercept form, we had standard form, we had vertex form, and we were just comparing all of those in this next section down here. All right, so that's what your homework will be like. As always, if you have questions, let me know. Message me on Canvas.